Hey guys, so welcome back again into another video. So today in this video we're going to talk about the insertion reactions. Insertion reactions, right? Okay, first I will talk you about some brief explanation about what this insertion means in most common manner, right? Okay, let's take an example. Basically, in insertion reactions, what happens is, let's say we have a metal center, right? Mn plus. So then it is connected to a ligand called X. So what happens is there is a L ligand, right? L ligand. Most oftenly it's connected to our metal center too. So let's like this. What happens is now this L ligand will break its bond towards our metal center and go in between our metal center and X. So this will be our new structure, new ligand. So this is the pattern of insertion reactions, right? This is the pattern of insertion reaction. What you need to know is you need to identify if in the question asks like you will be given a particular reaction, it will be asked whether this reaction is insertion or not. That's the type of question most common, right? So you need to identify whether reaction is insertion type or not. You need to have that idea. So look at this pattern, right? So in oxidative addition, a two ligands from outside will come into our metal center and bind it. In reactive elimination, two ligands from our metal center will be removed. But in this case, there are two ligands. Only one ligand will get inserted into our another ligand and metal center bond. That's the pattern. That's what you need to identify. So there are two types. I am just mentioning these two types. So we will go depths in our later videos and in little bit more information in next videos. So there are two types. There are two types of insertion reactions. The first one is, let's this 1-1 insertion. These are the pretty simple ones. So what happens is, like, let's say we have a metal center and carbonyl group, and also we have a ligand like methyl group. Okay, now when the reaction happens, what happens is this carbonyl group, right? This carbonyl group and now methyl group will bind together to form this kind of ligand. So now there maybe you are having some questions like whether the carbonyl group is breaking the bond and going to a methyl group, or methyl group is breaking the bond and going to a carbonyl group. In for that we will come into our in this video. We will explain it in this video in later part. So hang on with me. And the second type is 1-2 insertion. 1-2 insertion. In this case, I will take an example like this one, cobalt. Here we have this one, and we have ethyl. So when the reaction happens, here we have our NO group and ethyl group, and also a new ligand will be formed. New ligand will be added. This is pretty much from the outside, right? So these are the main two types of insertion. Like I don't want you to understand these two insertion types. Like there are so much details about it which we won't talk about in this level. So I will talk about in separate video, because I need to, this is a little bit depth, right, in depth of chemistry. So I want a separate video to talk about this. So basically there are more details like what is this one mean, what is this one mean, what is this mean, what is this means. Likewise it's more complicated. So I will take another separate video after I've done with this playlist. So in that video I will explain everything about these insertion types. So for now, right, for now what you need to understand is you need to have a ability to identify a particular reaction, whether it's an insertion one or not, and also you need to understand the mechanism. So we will talk about the mechanism next. Okay, now to understand the mechanism, right, there are three experiments which have conducted through various scientists along our history. So let's talk about our experiment number 1. So in experiment number 1, so this is the pretty much the reaction which the scientist has done to observe whether the direct insertion is possible or not. So what's the direct insertion mean? So in this case, I have told you that most often our insertion reactions happen through like this pattern. So there is a ligand like over here, so it will break its bond and go in between our metal center and X. So you may wonder, like, why can't we introduce a ligand from outside and directly get inserted between our metal center and X? So this was the point which have experimented in this reaction. So we have a carbonyl ligand which is labeled carbon 13, right? This carbonyl ligand is with carbon 13 isotopes. So when this reaction happens, always the 100%, the reaction result was like this, right? This was the result. Like, you would never expect a carbon 13 at this point. The insertion never occurred from our outside ligand. Always it's from normally that the insertion happened with this methyl group, right? So always the insertion happened with the cis carbonyl group to our methyl group, right? In this experiment, what you need to know is the direct insertion is not possible, right? The direct insertion is not possible. The outer ligand here, right? This outer ligand never move into the direct insertion with our methyl group, right? Here you can see, like, always our carbon 13 labeled group is attached next to our newly formed ligand. So the direct insertion is not possible. In the next experiment, right? So let me draw the structure. So this is the second experiment which the scientist has conducted. So in this case, what they have done is they have converted the inserted carbonyl group into a labeled one by carbon 13 and heat it up to remove a carbonyl ligand, right? To de-insertion, to undergo the de-insertion, basically the reverse of this particular reaction, right? So when they are doing that, they have observed the 100% of their product is this. So the removed carbonyl is not the labeled one. So in that case, right, in that case, they have identified, right, they have identified the methyl group is always cis to this particular carbon 13 ligand, right? The methyl group is always cis. So what we can tell about this, like, what is the final information which we can get from this particular reaction, which is like this methyl group, right? When the de-insertion happens, this methyl groups always repels, right? Always removes a neighboring carbonyl group. It doesn't repel this particular labeled carbonyl group, because if that happens, if our label group is repelled from our metal center, then this won't be the 100% product we get, right? So 100% product, we have our label group in our complex, and also it's cis to our methyl group. So our methyl group should repel either this carbonyl or this carbonyl. It cannot repel this one, right? Because if that happens, the cis conformation or the cis orientation won't be occur. So it's always the repelled carbonyl, this repelled carbonyl, right? This repelled carbonyl is either this one or this one. That's the main information we can get from this experiment number 2. You need to understand that. So we have gathered two information. The first one is when the insertion happens, the direct insertion is not possible. There won't be a direct insertion. And when we are conducting this particular deinsertion type reactions, right? Deinsertion type reactions, always the carbonyls or ligand which is cis to our particular acetyl group will be repelled. That's why we get 100% of cis product. And then let's move into our final experiment, experiment number 3. Okay, so let me draw the structures for this. Okay, this is the last experiment which they have done to observe the insertion type reactions, right? So again, a deinsertion type of reaction carried out. So we have two products in 1:2 ratio, right? In this reaction, you can see like the thing is they have concluded when the insertion in this reaction, in particular this reaction, this is a deinsertion type. So in this insertion type, the methyl group here, this methyl group have to leave by breaking this bond, and then it has to repel one of the carbonyls from our metal center. That's the information which they have gathered from this particular reaction. The thing is, if we think that in otherwise, so if we think that the carbonyl is removing, right? Carbonyl is this inserted carbonyl is being removed from our metal center. You must have a product which is 100% cis between this methyl group and this carbon 13 labeled one. But we won't able to achieve that. You can see that this is the particular product which we would expect if the carbonyl is the one who leaving them, right? If this carbonyl group is leaving our metal center, then this methyl group will directly attach to our metal center. So you can see it is always cis to our carbon 13 labeled one, but which is this product. But this is not the case, right? Because we have another product. So this product cannot be achieved by removing this particular inserted carbonyl group. So the carbonyl group won't be the one which is leaving the metal center. So it should be methyl group which is attached to our ligand, or which is attached to our carbonyl group is the leaving, and then repels another carbonyl group across our metal center to bind again to our metal center. So in this case we have concluded the methyl group is the leaving component in this case. So we can take this information into reverse form, right? So if we have a metal center like this, so let's say methyl group over here, we have a carbonyl group and another many ligands. So when the insertion happens, right? When the insertion happens, the reverse of deinsertion, right? In deinsertion, you can say that methyl group is leaving, right? Methyl group is leaving, and then again it will attack to our metal center. So in this case, methyl group will break its bond from our metal center and then attack to our carbonyl center to form the COMe group. When it comes to the reverse, this methyl group will be removed from this and then again attached to our metal center. So these are the observations we have obtained, right? The other thing you need to understand is these are 3 reactions, right? These are 3 reactions. So we have 3 observations. These are 3 reactions with 3 observations. So we will talk about these things and these theories a lot more on next video. So I hope you get the main idea about the insertion reactions, right? So let's move a little bit forward with some examples. Okay, so let's look at this one. So we have LN M. So this is some types of ligands, right? There can be carbonyls, any ligands, right? I just commonly denote it as LN. So this is connected to a hydrogen atom. So what happens is we are going to react this one with ethylene. Sorry, not ethylene. Just take a common. Yeah, just take a common alkene, just like this. Okay, now what happens is the first step would be our complex would form the bond with this alkene, right? As you know, like from our conclusions from our from our conclusions with that 3 experiments, you know that the direct insertion is not possible, but the direct insertion is not possible. So the first step must always, the inserted ligand has to be connected to our metal center, and now then we can have the insertion. Now we can have the insertion with hydrogen coming into our alkene group. So LNM CH2 CH2. This is our final product, right? This is our final product. So there are some few points you need to understand about it. So let's go by one. The first thing is, you can see there are no change in formal oxidation state. If this has oxidation state of plus N, then the same oxidation state, which is plus N, will be occupied over here too. So no change in formal oxidation state. We are talking about the metal center, right? And the second thing is, always that when this insertion happens, right? When the insertion happens here, when the 2 ligands are getting through the insertion, they have to be cis to each other, right? 2 ligands have to be cis to each other. If it's not cis, then our complex should have the ability to reorient it into cis form. So again, in the next point, we can say there are, like, when this process is happening, right? When this process is happening, you can see in this case we have added a new coordination site, right? The coordination number has increased by 1, and again when the insertion happens, again coordination number reduced into 1, which is the same as our initial compound. So a new vacant coordination site would be created when the insertion happens. So new vacant coordination site would create it. And finally, right, when finally we can say the coordination number of our initial complex, right here, initial complex, and our final complex is not changed most of the time, right? Most of the time, but there can be some unstabilities. So if our solvents and ligands give enough condition to be stabilized by adding a new ligand to here, then it would go through that direction. But in this case, most often the coordination number would be unchanged with our first, like, initial compound and our final product. So coordination number is unchanged, but in the between of the reaction, right, in between the reaction, you can see the coordination number has increased by 1 and again reduced by 1, but the overall it's not changed. So I hope you get the idea about the insertion type reactions, right? So in the next video, let's talk about beta hydride eliminations, which is another interesting topic.